Welcome to this new video where we'll analyze two solutions to the peak finding problem. What does the problem say? The problem says, given a non-empty array of integers r, create a function that returns the index of a peak element. We consider an element as peak if it's greater than or equal to its neighbors, the next and previous element. Assume that r of -1 and r of n are equal to -infinity, and if there are multiple peaks in r, just return the index of one of them. For example, if we have the array 6, 4, 5, 8, 3, 7, we have three valid outputs. We have the index 0 because 6 is greater than its left neighbor, which is considered -infinity because it doesn't exist, and its right neighbor, 6 is greater than 4. The second valid output is 3 because r of 3 is greater than its left and right neighbors. And the third valid output is 5 because r of 5 is greater than its left neighbor and greater than its right neighbor, which is considered -infinity because it doesn't exist. The first solution is obvious. We just traverse all the elements while searching for a peak, and as soon as we find one, we return its index. Okay, but how can we identify a peak? We said that an element is a peak if it's greater than or equal to its neighbors. So r of I is greater than or equal to r of I minus 1, and r of I greater than or equal to r of I plus 1. But this condition doesn't handle edge cases, the first and the last element. To do so, we write is the first element or is greater than or equal to the previous element, and is the last element or is greater than or equal to the next element. Now we traverse elements of R, and if one of them respects this condition, we return I. We can be sure that we will find a peak because a non-empty array always contains a peak. This is why we don't need to return something after the loop. We can be sure that some iteration will return I. For the time complexity, here we are just traversing elements of R while doing O of 1 operations inside the loop. The time complexity is O of n. And for the space complexity, we are not using input size related extra space, so it's constant, O of 1. What if I tell you that we can solve this problem in O of log n time? We can do so by using divide and conquer, the technique we used in binary search. The idea of this second solution is that we directly go to the mid, and if the element at the middle is smaller than the next element, it means that we have an increasing sequence of elements, so we search in the right half only. Because in an increasing series of elements, we always have a peak. Let me tell you why. We found the beginning of an increasing series of elements. Now we have three scenarios. The first one is that the series decreases at some point. In that case, here is the peak. Second scenario, the sequence becomes stable. In that case, here is the peak, it respects the condition. Third scenario, it keeps increasing until the end of the array. In that case, the peak is the last element because it's greater than or equal to its both neighbors. Remember, r of n is -infinity. Okay, but what if the element at mid is not smaller than the next element? In that case, it means that we either have an increasing sequence of elements from the right that starts from the index mid plus 1, or a stable sequence of elements. For the increasing sequence, we've seen that we always have a peak, and for the stable sequence, we also always have a peak. Here are the three scenarios. When the stable sequence increases at some point, then we have an increasing sequence. We know that it contains a peak. When it remains stable, then each element in the stable sequence is a peak, because it's equal to its neighbors. And when it decreases, then the first element of the decreasing sequence is a peak. So when r of mid is not smaller than r of mid plus 1, we're sure that we will find a peak in that sequence, so we search in the left part only. In code, same as in binary search, we use two pointers left and right that represent the boundaries of the part where we're searching for a peak. At the beginning, we're searching in the whole array, so left starts at the first index and right at the last one. Now while left and right didn't meet yet, we calculate the middle index, which is left plus right divided by 2. Then if r of mid is smaller than r of mid plus 1, then there is a peak in the part that starts at mid plus 1. This is why left becomes equal to mid plus 1. Else, it means that there is a peak in the part that ends at index mid. This is why right becomes equal to mid. After the loop, left and right are at the same position, the position of a peak. We return one of them. We can return left, for example. For the time complexity, same as in binary search, we are dividing the input size by 2 at each iteration, and we stop when we have only one element left. So the number of iterations is the number of divisions by 2 to go from n to 1, which is log 2 of n. And inside the loop, we are doing O of 1 operations only, so the time complexity is O of log n, where n is the length of R. And for the space complexity, we are not using input size related extra space, so the space complexity is constant of 1. We reached the end of this video. In this one, we've seen an interesting solution that uses decrease and conquer to solve the peak finding problem in of log n time complexity. I wanted to include this problem to show you that knowing techniques like divide and conquer, dynamic programming, greedy algorithms can help you find a solution that has a better time complexity. I hope that you understood both solutions, and see you in the next one.